Okay, welcome back. So now we're moving on to another simple piece of geometry called the angles of a triangle. Okay, so we may name the angles in a triangle with capital letters. Just to recap, just to remind ourselves, so the opposite side to angle B will be B, opposite side to angle C will be little c, and the opposite side to angle A will be A. Now these are not, you could then argue as well that the point here is A, capital A, the point here is B, and the point here is C. Okay, now I want you to think about taking any side and extending it. Okay, and when you do that, you extend the side. It goes from a line segment to being a ray going on that way. Then we can talk about this external. Okay, they're calling this C, but we can talk about this external angle. Okay, this is a pity now because there was C here and now they're calling this C. That's quite unfortunate. Let's call it D, will we? Okay, because this we had said is C. Okay, so we've angle D here. Am I using the right capitalization? No, it should be a capital D. Okay, so let's define this as being capital D. This is capital C. Okay, so now I'm going to give you the proof that the external angle equals the sum of the two internal angles. So let's do some exploring. And I'm going to do a lot more exploring here. So imagine that we draw this line in here that is parallel. So these are your theorems and your proof. So I'm proving to you first of all that these three angles add up to 180. Okay, so basically we're drawing a parallel to our base. Done. It's a line parallel to our base through the vertex at the top, the apex of the triangle. And so then I can call this C because they're all... no, I can't. I can call this A because it's alternate to this A. And what can I call this? I can call this C because it's alternate to this C. That's a transversal. This is a transversal. Okay? I could extend the baseline on if I wanted to. Don't stop me. Oops. What went wrong there? What's going on? Okay. So then we're going to use the straight angle property that A plus B plus C equals 180 degrees. And I rest my case because now we know that these three add up to 180 degrees. Okay, so we've proved it. It's somewhere out there. It's one of the theorems we have to be able to prove. We'll come back to it later, but now's the time to do it. Similarly, so we know that A and B and C internally here add up to 180. A, B, and C add up to 180, and we know that C plus D adds up to 180. So if C and D is 180, equals 180, and if A plus B plus C equals 180, well then D and A and B have to be the same thing. D is equal to A plus B. Do you see why? Okay, because they're in the same place, taking up the same, have to be making up the same value as 180 minus C. Okay, that's my proof. So an external angle of a triangle is equal to the sum of the interior opposite angles. You want to write that out several times, okay? And we'll be understanding how to apply it. Okay, in an equilateral triangle, every side is equal length and every angle is equal length. So it would be very wrong of me to fly past this. I'm going to show you some material which is going to really whet your appetite, and it's going to start getting all our geometry done. So I want you to take out a copybook, take your geometry set, which is all dialed in, ready to go. Remember, I showed you a video on how to get your geometry set ready for action. Just bring a pencil in here and just follow along with me now what I'm going to do. Okay, just for the interest of scaling, I'm going to say to you, will you please draw a 3-inch line segment on plain white paper or into your copy along a line if you want to, but it's not important. So that's from 1 to 4. It's only ballpark. Okay, now when I draw my line segment, I'm going to put the endpoints on it. Okay, I'm going to take out my compass and open it left to right. Arc up, an arc up, mark the intersection point of the arcs. Now look what I'm going to do here. I'm going to stay anchored and twist. Okay, so there's a knack to drawing lines and line segments. Okay, and that's an equilateral triangle. This is a unit, 1, 1, and 1. Okay, and we have 108, and because of that we have 180 degrees divided by 3 equals 60 degrees, because every angle opposite the same length side is the same. Okay, so that's our equilateral triangle. Just spell it from the book, equilateral. Lateral is on the side, or the side. Equilateral triangle. Done. Okay. Now we want to make a 45-degree triangle next, and we're going to do that in a really simple way. We're going to be bisecting. Actually, sorry. Okay, let's take that one step further now. We're going to do it all again, but we're going to do it in a more interesting way. So halfway down here, I'm going to go with halfway down my sheet. I'm going to go back to my 3-inch long ballpark. Now it's not important that it's exactly 3 inches. Okay, and I'm going to do this again, but this time I'm going to create a perpendicular bisector. So basically we're going to do a semicircle off that one, and a semicircle off this one. Okay, and we're going to produce a rhombus when we join them all up. There's an intersection point here and an intersection point here. So again, you can keep an eye on what I'm doing here. I'm anchoring there, I'm twisting around, I'm coming up here, and this is the last bit here to go. Okay, that's a rhombus. This is the exact rhombus I've made up essentially here. Okay, because we've got an equilateral triangle and an equilateral triangle. Or more importantly, ignoring the two diagonals, the major diagonal, which is yellow, and the minor diagonal, which is red, we have a rhombus because all of the red lengths are the same length. Okay, and then one of the most interesting properties of a rhombus is that the diagonals intersect at 90 degrees. Okay, so when I join these two together across here, I form the second diagonal, and sure enough, I don't need a protractor to show it. I can just take a set square, and sure enough, that is 90 degrees. Okay, so that's really interesting, and it produces something really interesting. So follow my drift here. So if this is 1, then this is a half. So let's actually go the other way around. Let's call this 1, because when we talk about units in geometry, we can make this equal to 1. And then if this is a half of that, then this is 2. Okay, which leaves the third side of this 30, 60, 90. So what I have here is I have this triangle. Okay, I'm facing it the other way around, but that doesn't matter. Okay, I have this triangle twice, like so. I'm going to go a bit higher there, but that's what we have. Okay, and so what I have here is I've made a 30-degree angle. I've obviously got a 60-degree angle here because this was my original equilateral, and 90. And now I can use Pythagoras to go with the square root of 2 squared minus 1 squared, or the square root of 3. Okay, so we've got this terribly important triangle. It's going to be used an awful lot, where you go 1 is to 2 is to root 3. And notice that root 3 is smaller than 2. You can do that in your calculator, it'll come out to be less than 2. Okay, really important. Now the 45-degree one, I'm going to do a bit of a trick on this. And that is, so we'll create a working line. What is a working line? It's just you're not sure what length you want or anything, and it's just get a line. It's called a working line because it just gets you started on any project whatsoever. Now I told you I won't be using the this one much, but we're going to use it here. Okay, now a trick on using the set squares is just to use them to start your lines, and then to bring in your ruler or your straight edge to complete them. And don't worry about that bit sticking up at the end. Construction lines are important, they're part and parcel, and we don't take too seriously about rubbing out the bits or anything like that. It's not technical graphics, okay? But that there is an equilateral. Now I just want to show you something else. I didn't have to, so could I have gone without the working line? I could. Okay, but so just finish this out. What I did there, this is 1 is to 1, and then this is a right angle, so we're getting the square root of 1 squared plus 1 squared when we're doing our distance formula, or the square root of 2. Okay, but I want to do it again in a simpler way. It's not even use a working line. Okay, so I'm going to come in here again with this and just say, can I get a 45 degree angle? And that's my 45 degree angle. At least it will be when I extend those line segments. So extend it on this way. That's a line segment I've drawn, and I'm going to extend it on so that it intersects with the other line segment. It intersects. Okay, so all I know about this is that's 45 degrees. That's the only thing we know so far. We pick up our compass. Okay, and we'll mark 2 lengths that are equal in length. Okay, so that equals that. And we take our intersection points and draw them across. So it's the same result as the last time, only I've gone about it in a different way. I didn't start with my working line. But what's important about this, it's isosceles, because this equals this, and it's also a right angle. So this is our right angled isosceles triangle. That's what that is there. Okay, if you want to draw it real quick, you use the inside, and it's 1 is to 1 is to root 2. So let's look at 45 degrees. Well, hold on a minute now. If I come along here like this and draw in a perpendicular, and a perpendicular is a line that comes up here at right angles and cuts the vertex, then I've created a baby, haven't I? A little baby 45, 45, 90. I've created a baby right angled isosceles triangle. Okay, and so let's just see where we're going with scale here, with numbers. Well, I could have called that 1 is to 1 is to root 2, but I can also come in here and call that 1 is to 1 is to root 2. The important thing is that whatever number this is, the call is 2 and call is 2. Is that fair enough? Because they're the same. Well, then this has to be 2 root 2. We just do another one, even though it's not, so it's not to scale because it's clearly not on the same scale. If I put 7 here and 7 here, then this is 7 root 2. Okay, so that's just a little bit about triangles, and we can do things like find out the cos of 45 degrees, because we can go adjacent, which is 1 over root 2. So we get the cos of 45 is 1 over root 2. We get the tan of 45 degrees is 1 over 1, and so on. Okay, I hope I haven't messed up your video by making it extra long compared to what you were expecting, but it's kind of important. Okay, so and another thing here is, so we're going to say, how do we draw an isosceles triangle, and how do we draw our right angle triangle? So to the isosceles triangle, we would just define this as let's again use inches, so that I can give you a guideline. Give me a 2-inch line segment. Never start at the 0, it's tricky. Start at the 1, drive it out as far as 3. Okay, so this is my base. Take your compass, I'm only putting this out here because I kind of want to give you a sense of what is your opening. So that could be your generic opening, so it's open the same amount as your protractor. Okay, and then we call anything less than that kind of a short opening, and anything over that would be a long opening. Okay, so we keep it but it doesn't really matter here, but I just want to give you that kind of scaling of your protractor. So I'm going to mark the endpoints. It's just a kind of an extra little thing to say these are my endpoints, and I'm going to draw in an arc. Now I'm not using this length. That's the one length you don't want to use, because that would produce an equilateral triangle. So you want to extend it beyond that and draw it up, and then switch it over symmetrically to the other side. Now I do find this ruler tends to be too long and go all over the place, so we're going to be using our shorter ruler the vast majority of the time. Draw in your intersection point and join them up. Leave this anchored here now and twist back over here. Okay, and this is called the vertex of an isosceles triangle. So you have a load going on here. You've got the base, which is the base side. You've got the vertex corner, but the vertex means corner, so that's the vertex, that's the base side, and you won't see the word side that often. The whole yoke is called isos. That's palindromic, SOS either way. CELE, isosceles triangle. Okay, these are called the base angles because they're on the base and they're equal. Okay, we might say B and B. The base angles are equal, and this is called, guess what, the vertex angle. Okay, so the two base angles, 2B plus V, together form 180 degrees. Okay, so we can do a lovely bit of algebra here and say, so the vertex is equal to 180 minus two bases, or it's double 90 minus a base. Okay, so if you have a base is 20 degrees and you have to find this angle, you'd go 90 take away 20 is 70, double it is 140. So I've drawn that all wrong, but that would be 140. I've drawn that, didn't draw that scale at all. The other thing we could do here is make, and this is good solid algebra here. So here we made V the subject, and now we're going to make B the subject. How do we make B the subject? We're going to transpose the V term, get 2B equals 180 minus V, and now we're going to divide down the double factor. So B equals 180 minus V over 2. Okay, and we'll be using that as we go forward into the textbook. Last one there is a right angle triangle. And while we can do it all sorts of ways, let's just start off simple. Draw yourself a right angle. Extend it. Take your compass, and we'll just do a generic one. Now, by the way, sometimes in the course you're going to need the a leg and a hypotenuse. So let's say we want the leg to be 3 and this to be 4. And if it was 3 inches, you could measure it out 3 inches against this. But really, that's not that important. If we want it to be 3:4, we could just go. Yeah, sorry. Let's go with 3 and 4 off this. So that's 3, and that's 4. And it's as easy just to do them separate and place down your things. It looks like excess, but it's not. Okay, and say I want that to be 3. Done. I want this to be 4. Now I'm pushing out towards the end of my limit here, and that doesn't quite cut, so that's okay. We can extend up. And that's a nice, and one of the more difficult constructions we're doing in the course. You've seen it already, so when it comes to it later on, we'll fly through it. That's a 3, and the hypotenuse is 4. Okay. Of course, if we're making a right angle triangle with, let's say, 2 here and 3 here, it's very easy. You'll put down a length, and they'll give you half of this stuff anyway. You'll put down a length of 2, that's 3, sorry, and you'll put down another length of 2, and you'll say I want that one there heading out that way. I'll extend that in a second. And you want this one here up that way, and I'll extend that in a second. Okay, so the two legs is even easier than going for the right angle. Right angle triangle with the two short sides 2 and 3 is defined there, and you can join that in. Okay, so we can do anything, and then we can use the protractor to make an angle. You're going to have side angle side, and you're going to have angle side angle. More of that later, but it'll whet your appetite and see how lovely geometry is. Okay, video's still running. We're 20 minutes in. We love the maths, and we're driving on. Whoops, easy. And we're on here, and we've done all of that stuff for right angle triangle. In a right angle triangle, of course, you've thing, and these two sides here make up a right angle. Okay, skip that investigation. I've probably done it already. So we're getting into this first example here, which is taking a quadrilateral that happens to have an equilateral triangle here. It's all defined there in the drawing. Let's get straight into it and find the angle that runs from M to N to P. So you have to trace this out from M to N to P. Find this angle. Okay, well, you take note that these are parallel. This is a transversal, and therefore if there's 29 here, there's 29 here. Okay, so we didn't have to find it, we had to write it down because it was already given to us. So 29 degrees, and our justification here is that they are alternate. So that'll be your justification, alternate, 29 degrees goes there. Next up, from P to N to, from P to N, from P to M to N, from P to M to N. Well, here's our, this is just what I was talking to you a minute ago. This is my isosceles triangle. Okay, so you have the vertex angle plus double the base equals 180 degrees. Okay, so we have a base of 29, so I'm going to go to the calculator now and start the calculation, or better still, write it down. We're trying to get the vertex, so the vertex is equal to 180 minus double the base angle. Okay, that's written down there for us now, and we're heading into the calculator. Clear it. The entire triangle of angles minus the two bases minus 2 by 29. Okay, equals 122. And we just checked that they got them right at the back here. They got 29 degrees and they got 122. And we'll do the exercises in the next video. As always, see you in the next one.